Chemistry. This lesson deals with discovering the atom. So the Bohr atom. An orbital, also called a shell, is an energy level at which electrons must stay. Electrons can pass from one orbital to another, but cannot stay in between orbitals. Niels Bohr came up with the idea of circular orbitals about 100 years ago. You will learn later that the shape of the orbitals are more complex than this. Electrons in orbitals further from the nucleus have more energy. In other words, they're able to repel the pull of the protons in the nucleus, and so they can fly further away from the nucleus. Orbitals can be compared to steps on a ladder. You can climb up or down steps on a ladder, but you can't stand in between steps on a ladder. In 1897, J.J. Thomson discovered the electron. Thomson placed a negative plate and a positive plate at opposite ends of a cathode ray tube, which caused a stream of electrons to move across the tube. By placing a magnet on the side of the tube, he caused the electrons to curve. He was able to determine both the mass and the charge on the electrons. So there is the negative end. That's a negatively charged cathode. That's going to repel negatively charged electrons. On the other side is a positively charged plate called an anode that attracts the electrons. So the electrons are going to fly straight across from left to right. This creates a visible stream of electron gas, as you can see in picture number 3. And a magnet causes the negative electrons to change directions. And based on how much that magnetic charge was, he was able to determine the charge on the electron and the mass of the electron. In 1904, Thomson proposed a model of the atom that included electrons. He knew that there must be positive charge to balance the negative charge of the electron. He believed that the positive charge was evenly distributed in a sphere with the electrons spread around the sphere. This model became known as the plum pudding model of the atom because it was a soft, solid sphere with chunks of electrons in it. So you can see plum pudding is not what we think of as pudding in England. It's kind of like a bready, kind of a cake substance that's made with spices but in this case you stick chunks of plum in it. So that's what they kind of likened his model of the atom to. In 1911, Ernest Rutherford performed his gold foil experiment. The experiment demonstrated two things. One, an atom has a solid nucleus center, but that most of an atom is empty space. In other words, it's not this big, soft, squishy, positively charged sphere. It's basically a solid, positive nucleus, very small, very solid, where all the positive charge is, and the rest of the atom, where the electrons are, is empty space. Rutherford shot alpha particles, positive charges, at a thin sheet of gold foil. If Thomson had been correct, the alpha particles would have shown a small deflection. In fact, most showed no deflection, and some, and this surprised Rutherford, bounced back. This indicated a solid nucleus surrounded by empty space. So there we see alpha particles flying from left to right through the gold foil. Positively charged alpha particles, most of them miss. Most of them don't hit the nucleus, such as the one at the top there and the one at the bottom. Occasionally one will come very close to the nucleus, and since alpha particles have a positive charge and the nucleus has a positive charge, they'll be deflected away from the nucleus. They'll curve away from the nucleus. And then occasionally a few hit the nucleus directly and bounce back, and that's what really surprised Rutherford. The discovery of the proton is credited to Ernest Rutherford, who proved that the nucleus of a hydrogen atom, i.e. a proton, is present in the nuclei of all other atoms, and he did this in the year 1917. In 1932, English physicist James Chadwick discovered a particle that had the same mass as a proton, but no electrical charge. This particle was called a neutron. Protons and neutrons each weigh about 1,836 times more than an electron. If you put the nucleus of a helium atom floating above the middle of San Diego Stadium, which no longer exists, but that's what it looked like, and the stadium were the atom, the nucleus would be 1 millimeter in diameter. That's one of those tiny lines on a meter stick. The electrons would be in the upper level. Most of the volume of the atom is made up of empty space. So there's the nucleus in the middle, and there's the electrons way up in the upper level. They might even be farther away than that. And the nucleus would be much smaller than what you see there. So the vast majority of an atom is empty space. An isotope is an atom of the same element but with a different number of neutrons. So here's a lithium atom, and it's called a lithium-7 because it has 3 protons. Lithium must have 3 protons. That's what defines lithium. We'll talk about that on the periodic table at a later time. And it has 4 neutrons. So the 7 means the total number of protons and neutrons is 7. What it really means is it has a mass of 7 atomic mass units. Since each proton has a mass of 1 atomic mass unit and each neutron also has a mass of 1 atomic mass unit, if you have 7 protons and neutrons, then the mass of the overall atom is 7 atomic mass units, and that's called its atomic mass. Now, electrons have mass, but they're not counted simply because it's so small that they just neglect electrons when they compute the mass of an atom. So just remember that. The mass of an atom is only computed by the protons and the neutrons. Now here's a lithium-6 atom. It has 3 neutrons, 3 protons. It must have 3 protons to be lithium and 3 neutrons. So that's a total of 6. So it has a mass number of 6. The notation for an isotope is, on the top is the mass number. It's the total number of protons and neutrons, which is also the mass of that particular isotope. And on the bottom is the atomic number. And the atomic number, we're going to get into that definition here in a moment, but that's the number of protons. That's what defines lithium as lithium. So the number on the bottom for lithium has to be a 3. The number on the top can be different numbers depending on the number of neutrons. The mass number, the mass of a specific isotope is on the top, and the atomic number, which defines lithium as lithium being a 3, is on the bottom. An alternate notation for an isotope is what you saw before, Li7. It means it has a total of 7 protons and neutrons, and it assumes that you know that lithium has to have 3 protons. Therefore, the rest of them have to be neutrons, the other 4. Lithium-6 also assumes that you know lithium must have 3 protons, so the other 3 have to be neutrons. Another way an isotope can be expressed is shown here. The atomic symbol is followed by the mass number. Ions. An ion of an element is an atom that has a different number of electrons than protons. So on the left you see an electrically neutral normal lithium atom. It has 3 protons, 3 positive charges, and to balance it out it has 3 electrons. All atoms are born electrically neutral, that they have the same number of protons as electrons. In the case of lithium, it's 3 and 3. Neutrons have nothing to do with ions. Now, if you look over on the right, you see the lithium, an ionized lithium atom. It's lost an electron. Why that happens is something we're going to talk about in the next few lessons. But now it only has 2 electrons, but it has 3 protons. That would mean this lithium ion has a positive charge to it because it has more plus charges than negative charges. Okay, so that's an ion. It has a different number of protons than electrons. The lithium atom on the left has 3 protons and 3 electrons, so the charge is balanced and the atom is said to be electrically neutral. The lithium atom on the right has 3 protons and 2 electrons and is a positively charged ion. An anion is an atom that has more electrons than protons. So here you see a fluorine atom. So this fluorine atom is an example of an anion. It has one more electron than proton. You can count them. It has 10 electrons and 9 protons. An anion has a negative charge because it has one more negative charge than positive charge. So this grumpy guy is a negative ant. That's the way to remember it. The anion is negative. A cation is an atom that has more protons than electrons. So here you see the lithium atom that we saw in the previous slide. This lithium ion is an example of a cation. It has 3 protons and 2 electrons, which gives it a positive charge. So this dude is a positive cat. So just remember the smiling cat, he's positive, and he's a cation. So cations are positive, anions are negative. The atomic mass of each proton and neutron is 1 atomic mass unit. And that's the number we're going to use for the rest of this class. We're not interested in 10 to the minus 31 or anything like that. And we're not interested in the fact that truly a neutron is slightly more massive than a proton. We treat them as though they have the same mass, and that mass is called 1 atomic mass unit. An element's rounded atomic mass number tells us how many total protons and neutrons one atom of its most common isotope has. So 1 proton is 1 AMU, 1 neutron is 1 AMU, and that will be our working definition for the rest of this course. The technical definition of an AMU is that it is equal to 1/12 the mass of a carbon-12 atom, the mass of a standard carbon atom with 6 protons and 6 neutrons. That would actually give you a number halfway between the actual mass of a neutron and a proton, but we're going to ignore that definition. You will not be tested on it. It is simply, it's simply the formal definition. An AMU gives scientists a unit of measure for mass on the atomic scale. However, it is not practical for lab calculations. So now we're going to look at an entry on your periodic table. So you should look at your periodic table, and it has these 4 parts to it. So the atomic number, this is the number of protons that an element has. It is the number of protons that gives an element its identity. So hydrogen must have 1 proton. An atomic number is also the number of electrons that an element has in its electrically neutral state. That is, when it's born. Electrically neutral means that the number of protons and electrons are the same. Atomic number is also called the Z number, so remember that. Atomic number, Z number are the same thing. The atomic symbol is the abbreviation for the element that is used in chemical equations. Atomic symbols are often based on Greek or Latin names, so the letters don't always seem to match the element name. Also, I should point out that atomic symbols are universal. So H is used here in the United States. It would be used in China. It would be used in Germany, in Mexico, anywhere. They would use H for hydrogen. The atomic name, this is the name of the element. Atomic names can vary by language. However, the atomic symbols, as I just said, are universal across languages. And the atomic mass, this is the average of the masses of all isotopes of an element. The atomic mass is the average mass of all isotopes of an element. This accounts for the decimal value. So let's just take a simple example. If 50% of the isotopes of an element have a mass of 3 and 50% have a mass of 4, then the atomic mass of that element would be 3.5. Okay, so it's the average of the masses of all the different isotopes, that is, different numbers of neutrons in that atom, of the different types of atoms of that element. Rows in the periodic table are called periods, and columns are called groups. Each period, each row, represents a new orbital. So the first row up there with hydrogen and helium has 1 orbital. All of the elements from lithium over to neon in the second row or period have 2 orbitals. The third row represents 3 orbitals. The fourth row, 4 orbitals. Fifth row, 5 orbitals. Sixth row, 6 orbitals. Each group, that is column, represents an additional valence electron. So all of the elements in the first column, from hydrogen down to francium, down at the bottom, have one electron in their valence orbital. So for hydrogen, that would be the first orbital. It has one electron in its first orbital. Lithium has two orbitals. So its valence orbital is the second orbital. It has one electron in its second orbital. Sodium, which is Na, has three orbitals. So it has one valence electron in its third orbital. In other words, its outer orbital has one electron. And so on. If you move over to the second column, everything beryllium, magnesium, calcium on down have two electrons in their outer orbital. So beryllium has two electrons in its second orbital. Magnesium, Mg, has two electrons in its third orbital. Calcium in the fourth row has two electrons in its fourth orbital, and so forth. Now you skip over the transition metals in the middle, that valley there. We move over to 3a, and boron, B, aluminum on down have three electrons in their outer orbital. Carbon, silicon on down have four in their outer orbital. Nitrogen has five in its second orbital, which is its outer orbital. Phosphorus, P, has five in its third orbital, which is its valence orbital, and so on. Oxygen on down has six in the outermost orbital. Fluorine, chlorine on down have seven in the outer orbital. And helium, neon, argon, except for helium, rather. Helium only has two in its outer orbital because it has only one orbital, but everything with two orbitals and beyond, 2, 3, 4, 5, 6 orbitals, has 8 electrons in their outer orbital. So now we're going to build an atom. You're going to learn how to read the periodic table and how to use that to know how to construct the diagram of an atom. So what you have here, we're going to use silicon as our example. It's in the third row, and it is the fourth element from the left. I've excluded the transition metals from this periodic table, so I've closed up that gap between lithium, beryllium, boron, carbon, or sodium, magnesium. The gap has been closed between the left side and the right side. I've just eliminated the transition metals. Okay, and then I have a scoreboard. We're going to keep track of how many protons, electrons, neutrons, orbitals, and valence electrons. Okay, and then we're going to draw a diagram in that open space there. That rectangle says protons and neutrons. That's the nucleus. I draw it as a rectangle so you don't confuse it with orbitals. So that's going to be the nucleus that has protons and neutrons, and then we're going to draw orbitals and place the electrons in the proper places in the orbitals. So here we go. So silicon has an atomic number of 14. That's the number at the top on the upper left-hand corner. So it has 14 protons and 14 electrons. So that number right there tells you how many protons, and when it's born, it's electrically neutral, so it has the same number of electrons. So we fill in our scoreboard with 14 protons and 14 electrons. Now we're also going to fill in our nucleus right there, and we see 14 protons right there. All right, now the electrons, we write the number 14 rather than drawing 14 circles with plus signs because that would be a little unwieldy. However, the electrons, we do need to actually draw them, so we're going to put them off to the side for right now. So there's 14 electrons over there. Okay, now we round the atomic mass to the nearest whole number. This is the mass of the most common isotope of silicon. Remember, there's no isotope, there's no single silicon atom that has a mass of 28.09. This is an average of the masses of all the different isotopes, that is, silicon atoms with different numbers of neutrons. So the one that's the most common is the one that is closest to 28.09. That is the one that has a whole number value closest to 28.09, and that would be silicon 28. Okay, so we're going to go ahead and round that to 28 like that. Now we're going to have to do a little bit of arithmetic here to figure out how many neutrons we have. So now we can calculate the number of neutrons by subtracting the atomic number, which is the number of protons, from the mass number, which is the total number of protons plus neutrons added together. So there's the mass number. It's protons plus neutrons, and we can see that that's 28. We just rounded that to 28. Then the atomic number is the number of protons. So, and that's 14. That's the number in the upper left. So if we subtract those numbers, 28 minus 14, we get the number of neutrons, which is 14. So now we can go ahead and fill in our scoreboard, and we can fill in our nucleus. So there's the scoreboard. Neutrons is 14, and nucleus neutrons is 14. So that silicon atom has 14 protons and 14 neutrons. Now, because silicon is in the third period row, it has 3 orbitals. So everything you see covered over in green there is in the third row. It has 3 orbitals. So silicon is among those elements. It has 3 orbitals. So now we're going to go ahead and fill in the scoreboard with that. There's the 3 orbitals in the scoreboard, and we're going to draw the orbitals. There's the first orbital, the second, and the third. Okay, so that's that. So we're getting there. Now the last thing we have to do is place the electrons. Now we could figure out the number of electrons in the valence orbital right now, but we're going to go ahead and place the electrons first. Okay, so here's how they place them, and you want to pay attention to this and do it exactly the way that I do it here. Okay, so we're about to place the electrons. So now we place the electrons. The first orbital gets 2 electrons. So the first orbital has 2 elements in it, hydrogen and helium, so it can hold 2 electrons. So there's the first, and there's the second. Okay, all other orbitals can hold 8 electrons. So the second orbital gets 8. Now watch how I place them. Oh, by the way, there's no vacancy there. You can't put any more in the first orbital. Now here goes the second. You're going to put the first one on the bottom. Then you're going to spread them out. Electrons are negative, so they want to spread out from each other. The third one's going to go on the top. The fourth one's going to go on the right. Now they have to start pairing up after the 4th electron. So the 5th electron is going to go down on the bottom there. The 6th electron is going to go there. 7th there. The 8th electron is going to fill up the second orbital. Now the second orbital is full. It can only hold 8 electrons. It has 8 electrons. So now that gets a no vacancy sign. You can't put any more electrons there. Finally, the final electrons are going to go in the third orbital. So the first one's going to go down there at the bottom. The second one's going to go on the left. The third one on the top. And the fourth one over on the right. And so the valence orbital, that's the outer orbital, which is the third orbital for silicon, has 4 valence electrons. Okay, so we're going to actually calculate that and show you that in a second. Okay, so we know that silicon has 4 valence electrons because it is the 4th element in its row. So without drawing this diagram, we could have known that silicon has 4 valence electrons. And sometimes that's all we want to know, because valence electrons are the ones that do the bonding, and we want to know how many of those we have. So here's how you know. You simply count from the left. Sodium is number 1. It has 1 valence electron. Magnesium has 2 valence electrons. Aluminum has 3 valence electrons. And finally, silicon has 4 valence electrons, which we can see from the diagram. So now we can go ahead and fill in the scoreboard, and there goes the 4 down there for valence electrons. And so everything is complete, and that's it for silicon. All right. Okay, so that takes care of a fairly lengthy lesson on discovering the atom and how you can read the periodic table to actually construct an atom.